there is a function fx and then I is the integral of that function. It's because this is too difficult to integrate. We have no idea how to integrate it. That's why we need to estimate the value. And then there are two methods to estimate it. Ada suggests the first method by using trapezoidal roots. BD suggests another system by replacing this one with the approximate function with two terms. And then in part A, they ask us to estimate by using both methods. Ada estimation is consider a curve and then cut it to 5 intervals. From 0.5 to 1, we have to cut it to 5 equal pieces. So each pieces, the width should be 0.1. So next one 0.6, 0.7, 0.8, and 0.9. We cut it to 5 regions. Originally, this is a curve, but we just simply connect 2 points to form a straight line, and this is trapezium. The area is not exact area of the curve, but it's quite close. So the estimation, we need few things. We need the height, f 0.5 here. We need f 0.6 until f1. So we write down f 0.5, f 0.6, f 0.7, f 0.8, f 0.9, and f1. In order to have 5 regions, of course we need 6 vertical lines to separate them. So then we just try to substitute it systematically. The first one, e power 0.1 times 0.5. That's why we have e power 0.05. This is 0.5. Second one, e power 0.1 times 0.6 divided by 0.6. So we have e power 0.06. Once you get the trend, you can finish it vertically. E power 0.07, e power 0.08, e power 0.09, e power 0.1, divided by 0.7, 0.8, 0.9, and 1. After that, you calculate this value and then put it into your calculator memory slot A, B, C, D, X, Y. Once you get it, you can finish your calculation. Estimation by Ada is equal to, first we have upper base plus the lower base, and the upper base of next one repeated, so this is 2 times. After we add all the upper base and lower base, we have to multiply the height of each trapezium. The height is equal to the width, that means 0.1, and divide by 2 from the formula of trapezium area. We get 0.74755967. We finished part of it. Now we are considering BD's estimation. It's just replace parts of our fx. It's become 1 over x times the 1 plus 0.1x plus 0.005x squared. And then separate the term. We have 1 over x, we have 0.1, we have 0.005x. Integrate it. We get natural log x 0.1x and also x squared 0.05 divided by 2 from 1 to 0.5. We use 1 case minus 0.5 case. Then we get 0.74502218. These two values should be quite close because both of them are the estimation of the same thing. Part B, we have to determine each estimate. Is that overestimated or underestimated? In part A, by trapezoidal rules, we are going to find out is the curve decreasing slope or increasing slope. If the slope is decreasing when x increases, that means the second order derivative d squared y dx squared is less than 0. And in this case, if we connect 2 points together, there are some space that we didn't calculate, so this is underestimated. In reverse, if the slope of the curve is increasing when x increases, then if we connect any 2 points, then we calculate more space than we need. Therefore, when d squared y dx squared is larger than 0, then our result is overestimated. For ADAS estimation, we are going to use this approach to test it. For BD estimation, we are going to consider those missing terms. And all those missing terms are positive. That's why we can prove that this is underestimated. So part B for IA. To consider the shape of this curve, we are going to focus on this part. Fx is equal to e power 0.1x and then x power -1. Differentiate the first time. Differentiate the first one. Keep the second one. And then we keep the first one. Differentiate the second factor. Tidy up the calculation. And then we are going to differentiate the second time. So the first one are exactly the same as our original function. So we just write down 0.1 and bracket, then we just copy down exactly the same thing. For the second term, we differentiate the first one. Keep the second one. And then we keep the first one. Differentiate the second factor. Handle it one by one. Extract common factor, and then we have 0.01 x -1, and then we have -0.2 x power -2, and last term we have 2 x power -3. Because we are going to prove that is that always larger than 0 or always smaller than 0, so we are going to extract common factor and factorize it. Extract common factor, we will choose the least power, so x power -3. And if I extract 100, then every term inside will multiply 100 times. So we have 1 x power 2, we have -20 x power 1, we have positive 200. In our given range, x is between 0.5 and 1. This is always positive, this is always positive. So the focus in what inside here. To know whether it's always larger than 0, we can by computing square. 100 e power of 0.1 x power -3. Then what inside is x squared minus 20x plus 100, and then plus another 100 without changing values. So this is what inside is x minus 10 squared and then plus 100. On top of a square, we add a positive value, so this is always larger than 0 for all x between 0.5 and 1. Since the second order derivative is larger than 0, so it should be overestimated. Write down the conclusion, then we now work on BD's estimation. E power of 0.1x, it should be equal to 1 plus 0.1x plus 0.005x squared, and then plus 0.1x power of 3 divided by 3 factorial, and so on and so on. All these terms which is missing are all positive value when x between 0.5 and 1. Therefore, the fact is e power 0.1x is larger than just 3 terms. Same conclusion when we divide both sides by x because x is a positive value in this range. Therefore, if we compare the integral, it's also larger than right hand side. That's why I is larger than IB. Our estimation, BD estimation, is smaller than the true value, which means that BD estimation is underestimated. Then we go to the last 2 points. It's quite easy. They say that the difference between I and this amount is less than this. Do you agree? So we are going to use a number line to write down the position of the true value and our estimation. If we compare the value of estimation from ADA and the value of estimation from BD, we will find that BD estimation is lower. So if we use a number line, the position is approximately like this. Now we are going to compare with 0.746. So 0.746 is between this. It's approximate here. Now the key point is based on our finding in part B. BD is underestimated, that means I is larger than IB. At the same time, A is overestimated, that means I is left hand side of IA. So maybe I may be somewhere around here. If we consider from this point more than 0.02, then the range is until here already, which is 0.748. Same reason, if we go back by 0.002, that this will become 0.744. And our possible region for A is between IA and IB. It won't exceed 0.02. That's why we should agree the claim that the differences is less than 0.02. When we formally present our answer, we should state clearly that I is between IB and IA. And we are going to compare it I with 0.746. So what we interested is the difference between I and 0.746. Then we both sides minus the same value. Right hand side give you 0.001555967, which is smaller than our 002. And left hand side we have negative 0.0009778.2. Again, it's less than negative 0.002. That's why the differences will not exceed this amount. Then we can agree the claim.